Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video, we're going to talk about normal distributions. One of the most common types of distributions is the normal distribution. And if you were to take a look at the histogram or the graph of it, it would look like this. It kind of looks like a bell, and it's called a normal distribution, or it will say that the variable is normally distributed. There are many variables or measurements that are normally distributed, and they vary depending on two parameters. One of the parameters is the mean. The mean is going to be right in the center of this curve, and the notation that's used for mean is the Greek symbol mu. You may be familiar with this notation used to represent mean, but that's in cases when you're dealing with a sample. With these distributions, we're talking about a population. So it's the mean for the population. This is the mean for a sample. And basically the mean tells us where the center of this bell curve or normal curve is going to be located on the x-axis. The other parameter that's important is the standard deviation. The notation for standard deviation is the Greek letter sigma. Again, this is the notation or the symbol that's used when we're talking about a population standard deviation. If you're looking at a sample, the standard deviation is just represented with the letter S. But the standard deviation, the size of it will determine how spread out or close together the normal curve is, which in turn affects the height of the curve. Let's take a look at an example of a measurement or a variable that is a normal distribution, and that is body weight of full-term babies. So the mean for full-term birth weight is 7.5 pounds, and the standard deviation is 1.1 pounds. So that tells us the mean birth weight for full-time babies would be 7.5 pounds. So most of them are going to be close to that weight, and fewer will be on the larger size, and fewer are going to be on the smaller size. All normal curves or normal distributions have the same properties, which we will now discuss. The first property is that it is symmetric about its mean. So the mean is going to be in the center, and the left side will be the mirror image of the right side. Second property is that the highest point of the distribution occurs at the mean. Next property is that the area under this curve will equal 1. So 100% of the population will be within this curve. The next property is because of the symmetry, the area under the curve to the right of mu, this area, will be equal to the area under the curve to the left of mu. And that each of those areas is equal to 1/2 because the total area equals 1. Next property says that as x increases without bound, so this is our horizontal axis, this represents x. So as x gets larger and larger and larger, the graph will approach 0, but it will never reach 0. It will never touch that line. Similarly, as x decreases, gets smaller and smaller, the graph approaches, but will never equal 0. So it will never touch that line. The sixth property that's very useful is called the empirical rule, and that tells us that approximately 68% of the area under the normal curve is between the x values of mean, the mean minus 1 standard deviation, and the mean plus 1 standard deviation. So 1 standard deviation is going to be about there and here from mu. So this is mu plus 1 standard deviation. This is mu minus 1 standard deviation. So 68% of the area under the normal curve is between that value and that value. So that means that 68% of the population will be between these two values. Another way to think of it is that area is equal to 0.68. The next part of the empirical rule says that approximately 95% of the area under the curve is between 2 standard deviations on either side of the mean. So this would be approximately mu minus 2 standard deviations, and and this is mu plus 2 standard deviations. So that area would equal 0.95. Or in other words, approximately 95% of the population will fall in that range. And the final component of the empirical rule states that approximately 99.7% of the area under the normal curve is between 3 standard deviations on either side of our mean. So mu minus 3 standard deviations and mu plus 3 standard deviations, and that's going to be 99.7% of the area, or 99.7% of the population, or has an area of 0.997. Let's take a look at an example using IQ scores, and I think you'll find it a little bit easier to understand the empirical rule. IQ scores is an example of a normal distribution, and we have a mean of 100 and a standard deviation of 15. So let's just put the 100 in there for the mean. That's the center point. And when we talk about IQ, that's going to be our X value. And if we want to apply the empirical rule, let's put some numbers. So one standard deviation is 15. So if we add 15 to our mean, we will get 115. If we subtract 15 from our mean, we will get 85. So that means that 68% of the area under the curve, or the population, will have an IQ score between 85 and 115. Now let's take a look at 95% of the area or the population, and we're going to add and subtract 2 standard deviations from our mean. So 2 times 15 is 30. When we add 30 to 100, we'll get 130. When we subtract 30 from 100, we will get 70. So 95% of the area, or 95% of our population, will fall in this range between IQ scores between 70 and 130. Then, approximately 99.7% of the area under the curve, or the population, will have an IQ score between, let's multiply our standard deviation by 3, which is 45. If we add that to 100, we get 145. If we subtract it from 100, we get 55. So 55 is 3 standard deviations less than our mean. 145 is 3 standard deviations more than our mean. So 99.7% of the area, or 99.7% of the population, approximately, will have IQ scores between 55 and 145. So hopefully that makes a little more sense for you. You might be asked to find percentages or areas using the empirical rule, and I'll just do one example of that. But in reality, we're going to need more than the empirical rule to do the calculations that you'll be required to do. But let's take a look at that example first. So an example of the type of question I'm talking about would be this. Approximately what percentage of the population would have IQ scores between 115 and 130? So we're trying to find this area. Now we know that 68% are between 85 and 115. It's symmetric. So if we take half of 68%, we get 34% of the area is here, which as a decimal is 0.34. We know from here to here, that's 95% of the population. So again, if we take half of it, this area is going to be 47.5%, or as a decimal, 0.475. So if I just want to find this area, I take this whole area, which is 0.475, subtract this area, which was 0.34, to get this area, which would be 0.135. Therefore, we could say approximately 13.5% of the population would have IQ scores between 115 and 130. The empirical rule can be quick and easy, and you don't have to use your tables or Excel to find some of your percentages or areas. However, in reality, you're going to be working with other numbers. Like I might say, what percentage of the population has an IQ between 105 and 140? So those numbers aren't relevant when it comes to the empirical rule. So in those cases, we are going to have to use tables or Excel to find those values. And in order to do that, we have to first learn about the standard normal curve, and then we have to learn how to standardize any normal curve so that we can look up those values via table or Excel. In my next video, I'm going to talk about a standard normal curve, so I'll see you then.